That works. Okay. Okay, good. So, any questions from last time? Okay, let's review a little bit of last time. Starting to get a little bit heavy here, all of this notation. So last time we proved this formula called the LSZ reduction formula, which relates scattering amplitudes, which is what we're interested in for experiments, to time-ordered correlation functions. So in particular, it tells us, and I'll just stick with the focus on two particles go to two particles scattering, okay? So they're momenta labeling the incoming particles, P1 and P2. And so we have an incoming state far in the past with momenta P1 and P2. And then we want to know what is the amplitude for that to convert into an outgoing state far in the future with momenta P3 and P4. And let me just first write down the answer, and then I want to discuss it some more. So the factor of I out in front, which is just raised to the total number of particles involved here, I to the fourth power in this case. And then we have a bunch of integrations over position coordinates. Basically, each of these is doing a Fourier transform to take you between position space, which is where our correlations live, and momentum space, which is where our scattering amplitudes live. So we need a bunch of Fourier transforms. There's no big deal about this. And you might hope that the answer would just be a Fourier transform of this 4-point correlation function. Just take this thing involving 4 particles, Fourier transform, and that would give you your scattering amplitude in momentum space. Okay, but it's not. You've got to take this and you need to multiply it by a bunch of Klein-Gordon operators. Okay? You can check, and in fact, one of your homework exercises is going to be to just check that this reproduces the 4-particle scattering, 2 particles to 2 particles in the free theory. You just get the delta functions that you need from this to reproduce that exactly.
So we don't have the 5 term here.
No, where?
So there's no interaction in this kind of.
No, I didn't even write down the Lagrangian here. In fact, this is valid for, oh yeah, here this is just the propagator thing. This is just, there's no interaction term in these operators here. It's just the free Klein-Gordon operator, okay? But this is valid for any interacting theory. I didn't assume it's lambda, that it's phi cubed or phi to the 4th. I didn't say what theory I was talking about at all. But it doesn't matter. It's true for all of those. So this is a pretty powerful formula here. Okay, because what it's going to tell us eventually is how to write this scattering amplitude in terms of Feynman diagrams.
The vacuum here is
And I meant the interacting vacuum. Sorry.
Action, the phi in action.
What's the other question?
Phi 1, phi 2, phi 3 in action, phi.
Where?
Phi x1. You could have phi I x1.
No, these are the full correlation functions. Okay. Remember that our formula for calculating correlation functions is you write down the correlation function for the full interacting fields on the left-hand side, and then we express that in terms of the interaction picture fields, which are like free fields, on the right-hand side.
We have assumed that the action is become less and less when the two particles separate together.
Yeah.
From each other.
Yeah, you're asking a good question. We'll come to that. Yeah. So I want to actually, what I want to do today is answer questions like that and some other questions. We made some big assumptions to derive this formula, so I want to discuss those assumptions today. Okay, and explain how to justify them. So these are the assumptions that we made. So first of all, we assume that the operator to create single particle states in the interacting theory had the same form as it did in the free theory. That's a huge assumption. Okay, so specifically, we assume that single particle states which I'll label by their momentum, are obtained by acting with, and this is to create a single particle state. Actually, I had an operator to create this at time t. Is obtained by acting with this generalized creation operator on the vacuum state, the interacting vacuum, where I wrote this in terms of the interacting field. So it's minus I integral d3x e to the minus I p dot x d0 phi at x. That's the definition of this operator A dagger. I chose that because this is A dagger in the free theory. And so now I want to just say, okay, I'm going to assume that the creation operator in the interacting theory takes this same form. My whole derivation was based on assuming this form for the creation operator. And assuming that that created exactly what I said, it created a single particle state. So that's one big assumption we made. And another assumption was, related to your question, is that two particle states are created, like P1, P2, are created by acting with AP, say at time t, with two creation operators on the vacuum state. Okay? Another huge assumption. It's perfectly true in the free theory, but in the interacting theory, you might worry, you're creating these two particles infinitely far in the past. How do you know they're not going to interact with each other a lot in this interacting theory? And that will change the form of the operator you want to create these states with. Okay? So, in fact, this second assumption really isn't valid the way we've stated it. Because if you're talking about momentum eigenstates for particle 1 and particle 2, those are completely delocalized. So these particles 1 and 2, we can't even think of them as being separated. They're everywhere in space. So they're constantly interacting with each other. So this is not the right thing to do. We're gonna, well, we had to do something. So now what I'm going to do is I'm going to add a little extra structure which will complicate this formula slightly. The reason I didn't do it sooner was I wanted to give you the simplest derivation possible. Okay? So how do we separate particles in real life? How do you take a momentum eigenstate and localize it? But suppose we wanted to have a particle that's here and not over there, that's in this general vicinity here. Maybe it's not exactly at the point x, but it's particle 1 we want to be widely separated from particle 2 over there. We make wave packets. Okay. So the way we're going to solve, so number 2 is wrong because particles, momentum eigenstate particles are delocalized, completely delocalized, so they interact with each other. And you can't speak of them as being separated, and there's no reason to expect the two-particle state will be simply made out of one-particle creation operators like this. So the way we solve that problem is to introduce wave packets. Fix it. So instead of creating a momentum eigenstate single particle of definite momentum, we're going to create an a particle of momentum approximately p, which is localized in the vicinity of, say, position x. Let me write this down for x equals 0. Okay, so I want to create a particle at the origin of space. So I'll do that by taking my various creation operators, all at time t, and taking a superposition of these which is peaked around momentum p. So for example, you'll take some function here called a smearing function. Which could be, for example, say proportional to, with some normalization, exponential of minus p minus q squared. We have to divide by some standard deviation over 4 sigma. That gives a, okay, so f of q looks like this. It's peaked around. That's how we make a wave packet. So this is the operator that creates a particle of momentum approximately p to within a width sigma, p plus or minus sigma, close to the origin. Within sigma of the origin. And that's really what I mean by a localized particle. When we think of particles in an accelerator, we don't think of them as being spread out infinitely over space. We think of them as being localized along the beam. So we've got some kind of thing that says they're in the beam, they're not way out here to the left and the right, so they're localized within the beam. And so we're using some type of wave packet to get all of these guys in a beam. Yeah, so if you wanted to put this at some position x rather than 0, what would you do? You would need to apply a translation operator to this, like e to the I p dot x. That would shift it by x, and when it hits this a dagger here, it will basically it'll multiply. It'll add a phase factor in this integral that looks like e to the I q dot x. When it hits that operator a, it will the translation operator will shift it by multiplying by e to the I q dot x. So this is what the amplitude to produce a particle at a general position x would be. Okay. So now, how does that solve things? So we create a wave packet way in the past and another wave packet way in the future, and now we can be assured these two particles are not overlapping or interacting with each other. So there's no problem of thinking of this two-particle state as really the product of two one-particle, widely separated one-particle states. Now, there's one issue with wave packets is they do spread out, right, in time. Wave packets spread. The radius of the wave packet will grow. Write this down.
Expectation value of this operator acting on the vacuum.
What's that?
So if we just act this A.
So this is the A we should act on the vacuum with to create a localized single particle state.
And we just calculate the expectation value of this particle. This wave packet. What should we get?
The expectation value?
Yes.
I'm going to calculate that. Okay? But let me say that you can now take these wave packets in here. So we had this incoming state, which was defined when t goes to minus infinity. And now this makes sense if we use here these spread out operators here. Okay? And we just give the particle we create at negative infinity some spread of momentum and a localized position way over there, and particle number 2 we make sure is coming from way over here. In real life, we might be colliding two beams from opposite directions. Okay? So now think of these operators here as really being wave packet operators peaked about P1 and P2. So now, so one claim is introducing these wave packets does not significantly modify the derivation of this formula. We're just taking superpositions of our original states here. And what will change is basically at the end of the day, you can take the width of the wave packets to be larger and larger so that these particles have momentum more and more peaked at P1 and P2. And so there's some limits that you need to take here, but there isn't really a problem. Essentially, these wave packets spread with time, as you know. The width of the wave packet, as you evolve it in time, spreads like, anybody remember? In general, it's t to the 1/2. It's almost like, it's like diffusion, in fact. Okay, so these wave packets gradually spread out. But the point is, the particles are moving, particles 1 and 2, are moving with constant relative momentum, or constant relative velocity. And so the particles are coming together and then after they collide, moving apart at a rate proportional to t. So they're moving together. Their relative separation is changing much faster than the spread of the wave packet. So we can basically ignore the spread in comparison to how fast they're moving together. Plus, you know, we're creating these particles way in the past at time minus infinity. And way in the past, they are basically infinitely far apart. And so we can make these wave packets quite large and the momentum quite sharply peak without having to worry about the particles overlapping. Okay. So there's a little bit more to say about how to take this limit precisely, but I think you can imagine basically what you need to do. You just have to make sure that you don't take the limit of definite momentum so fast that these wave packets get spread out too much. Okay. But once you take the limit of time goes to minus infinity, at the same time you can take the wave packets to be quite large in position space and quite narrow in momentum space. So that's the limit that we are considering in the LSZ formula, is the limit of sharply peaked wave packets which are delocalized in position space and sharply peaked in momentum space. Okay. So now we're thinking of our scattering process as being this incoming wave packet for particle 1, another incoming wave packet for particle 2, and as you evolve in time, these wave packets come together and interact with each other, and then for our outgoing state, we want to again have the amplitude for going into 2 wave packets. Okay, so that sort of takes care of assumption number 2. It explains a little more clearly how we're going to define these 2 particle states. We need to be very careful about how we define wave packets for single particle states, and then we can put them together to form 2 particle states. Assumption number 1 is a bit trickier to deal with, though. So how do we know in the interacting theory, here's assumption 1 again, in the interacting theory, in the non-interacting theory, we know that phi can only create from the vacuum a single particle state. It contains creation and annihilation operators. The annihilation operators do nothing to the vacuum, and the creation operators give you 1 particle states. But in the interacting theory, well, to a first approximation, you could expect, well, this will still create single particle states. But how do we know there isn't also, in whatever this creates, some component of a vacuum state or a two-particle state? Okay? And that's a really important question that we're going to actually have to modify the theory a little bit in order to make sure that this is what happens. Okay, so to understand this, let me just make some general comments about the spectrum of a quantum field. A general interacting quantum field. So, if it's relativistic, then we know that single particle states have it of definite momentum, like this. Which is called 4 momentum p. Have total energy equal to p squared plus m squared. I haven't really said anything here other than the fact that this is a relativistic theory. So there has to be this relation between energy and momentum. So that means if I draw a plot here of the momentum of a state versus its energy, it's going to look like this. The minimum energy is the rest energy is the mass of the particle. So now what about two particle states? Two particle states. Well, in a non-interacting theory, even in a non-interacting theory, the total momentum of a two-particle state and the total energy are not, in general, related by this formula here. This is only true for a particle, right? Because if you have two particles here, they could be moving relative to each other in addition to their parallel velocity. And that relative motion also contributes to the total energy. Okay? So even if you know that the total energy of or the total momentum of a system of two particles, like say they're coming towards each other with equal and opposite momentum, the total momentum could be 0, but there would still be non-zero energy. The minimum possible energy for a two-particle system is of definite momentum is when they're stationary relative to each other. So if these two particles are just sitting still, then the energy is equal to twice the rest mass of a single particle. And if they're moving along, then the energy obeys this formula compared to the total mass of the two particles. So let me summarize that. The minimum possible energy here for two particles is when they're standing still completely. And then their energy will be equal to the rest energy, 2m. That's not entirely true because in some cases you might form a bound state of two particles. That would reduce the energy, so there might be a bound state down here below 2m, but let's ignore bound states for now. And then if the particles are moving together, then they'll obey this kind of formula, but instead of m there, you'll have E equals p squared plus 2m squared. And that'll also be a hyperbola like this. And then what I was saying is they can have any relative motion relative to each other, and that is only going to increase the energy. It can increase by an arbitrary amount. So there's actually a continuum of states with energy above this hyperbola. This is a general picture of the spectrum of a quantum field theory, free or interactive. So it could be interesting stuff like, the density of states here would be different in an interacting theory than in a free theory at different values of energy. But the general picture here is true in any case. Okay, so for two particle states, the point is that the total energy is greater than or equal to the total momentum squared plus 2m squared. And that's what I filled in up here. Okay, there'll also be three particle states up here starting at 3m. And then there'll be a continuum of those, but those states are all inside of this continuum. So think of this whole upper part of the board as being a continuum of multi-particle states. Correct. Yeah. So the E total is actually equal to P1 squared plus P2 squared plus 2m squared. Okay? And I'm just making the statement that so the claim is then that P total here, which is P1 plus P2 squared, this is always going to be less than or equal to P1 squared plus, oh, that's not true.
I think the E total should be E equal to E1 plus E2. And for E1, just...
yeah, I'm sorry, you're right. That's right. This isn't right here. Yeah. So the point is that E total is P1 squared plus M squared plus P2 squared plus M squared. And this is always greater than that. Thank you. Okay. It's just some kind of Schwartz inequality or something. Okay. So, now that we understand that there are these various types of states. Of course, the vacuum is down here. The vacuum has no momentum and zero energy, the way we've defined it. So it's just a single point down at the bottom. Okay, so now what I want to do is I want to consider the effect of acting on each of these types, distinct types of states, with a creation operator. And see what I get. Or rather, no, I want to see is, I want to see if I act on the vacuum with a creation operator, whether I get any states of this type or of those types. I only want to get the single particle states here. So let's see what we have to do to make that be true. Okay, so for example, let's see if a dagger, actually to simplify things a little, I'm going to use phi, and I'm going to act on the vacuum. We can make the creation operator out of phi, okay? But the calculations are just a little simpler. I'm not going to have all these smearing functions and stuff. integrals over momentum. So let's just first see a slightly simpler problem, which is whether phi acting on the interacting vacuum will create just a single particle state or maybe some other states like vacuum state or multi-particle state. Okay. So see if this contains vacuum or multi-particle components. So for that purpose, let's see what is the overlap with the vacuum. If we calculate this, this will tell us what is the component of the vacuum when we act with phi on the vacuum. We'd like this to be 0. We'd like this to only contain single particle states. We'd like this to be a single particle state. So we don't want there to be any vacuum component. So we want this to be 0. Okay? But as we'll see, it's not necessarily 0. So first of all, let me show you that this is independent of x. This we can relate this to phi at position x equals 0 using translation operators. I'll put a hat over the p to remind you that it's an operator. And there. Zero, that's 0. X should be 0. Okay, so we've taken phi at 0 and we've translated using translation operators over to x.
We're going to want that thing operator. Translate.
Right. Okay, now the point is, what's the momentum of the vacuum? 0. Wouldn't be the vacuum otherwise. And so e to the I p dot x acting on the vacuum just gives back e to the 0 times the vacuum, just gives back the vacuum. The vacuum is translationally invariant. So that means that we get omega phi of 0 omega, which is just a number. It's a number that just depends on the parameters of the theory, like the mass and the coupling. It's going to be some function of those. Okay? So I'll give it a name. I'll call it V. V stands for vacuum expectation value. It's the expectation value of the operator phi in the interacting vacuum. So it should be 0, but on general grounds, it doesn't have to be 0. Okay, I can write down quantum field theories where it's not 0, in fact. In fact, the standard model has a scalar field that is basically the Higgs particle, which has a vacuum expectation value like this.
The interaction using phi4 is to
The interaction,
phi4.
yes.
It should be 0 for this value.
Oh, yeah, so that's true. But I don't want to assume that.
And phi cubed.
Phi cubed, it doesn't have to be 0.
If you say it doesn't have to be 0, it should be a constant, but that would just be considered the lowest state.
Yeah, and also for phi fourth, it also doesn't have to be 0 if you have a negative mass squared, which is what the Higgs particle does. Sorry, what?
No, I agree.
Okay. Okay, but for our, oh, and I should say, if you did have this, wanted to calculate this in a quantum field theory, it means that we're calculating Feynman diagrams with one external line. Okay? So Feynman diagrams like this. or with other stuff inside. Okay. So this is actually computed by adding together all Feynman diagrams of this type. These are called tadpoles, as I mentioned before. And tadpole diagrams are, well, if you run into a theory that has tadpole diagrams that are not zero, the prescription to deal with them, because they tend to be infinite and very annoying, is to shift them away. So what we can do, if we want this to be zero, is we can always take phi, so that this vanishes. So we'll define phi tilde of x, which is phi of x minus v, and then it's automatically going to be true that phi tilde will have a vanishing expectation value. What I had to do in order to satisfy this condition, which is required for assumption 1, is I had to redefine my field. Phi, well, this could be a prescription in phi cube theory to do this shift.
We have 3 particle states to phi cube.
3 particles? Oh, well, we're only considering vacuum goes to vacuum so far. We haven't considered vacuum goes to multi-particle state. But you're right. That could have something to do with the, say, the coupling constant for phi cube.
And so the shift should be different there.
Well, this shift here will, this is just one redefinition of the field. We're going to have to make other redefinitions of the field, actually, in order to get a theory that gives us what we wanted to give us. Okay? So let's just stick with this for now. The vacuum requires us to shift the field so that the tadpoles, the vacuum expectation values of the field, vanish. Okay. Now, let's consider one particle states. So in the free theory, now we're talking about creation of one particle state. So we want to evaluate the effect of acting with phi on the vacuum and whether that creates one particle state. In the free theory, it certainly does. And in the free theory, this would give us e to the, what is it, e to the minus or plus ip, I'm not sure. But anyway, it's something like e to the ip dot x in free theory. Okay. So in the interacting theory, let's do the same trick we did before. Let's move phi of x over to 0. This is p e to the I p dot x, or minus phi of 0 e to the I p dot x omega. E to the I p dot x acting on omega just gives back omega. Again, the vacuum is translationally invariant. And this we can pull out in front as e to the minus I p dot x, where p is this momentum here. Okay? So if this was the free theory, that thing would be 1, and we'd have this result. Good. So we really want this guy to be 1. In general, though, it's a number, just like we had a number over here. Okay. It's Lorentz invariant. Okay. Do a Lorentz transformation of this, and well, you can easily show. And if you do a Lorentz boost, that doesn't change the point 0 when you do a boost. Okay, so if you do a Lorentz transformation of this thing, it's going to be Lorentz invariant. Not translation, only rotations and boosts. Okay? Then this will be unchanged because 0 is invariant. The point 0 is invariant under boosts and rotations. So, but it depends on this momentum here, p. That's the only thing it depends on besides like the mass and the coupling constant. So it has to depend on p in a Lorentz invariant way. The only way you can make a Lorentz invariant quantity out of p is by p squared. Okay? So it depends only on p squared, but p squared is equal to m squared. So actually doesn't depend on the momentum at all. It only depends on the mass and I guess on the coupling constants, on the parameters in the Lagrangian. So it's just some number, call it z of m squared n lambda. We'd like this to be 1 so that the single particle states will be normalized correctly in the same way they are in the free theory. And so if we demand that this is 1, that's going to fix a normalization for phi. We'd already normalized phi in such a way that the kinetic term looked like this, with a 1/2 in front of it. Okay, now we're going to re-normalize phi. We're going to change the normalization of phi so that this matrix element will be equal to 1. So demand that is equal to 1. That's the same as saying we're going to now define a shift, a renormalized phi, which is phi of x, divided by this constant z. Okay. So once we change our normalization of phi, then this is true, and then we have the same equation that we had in the free theory. We have that this is equal to e to the minus ip by x. So we're creating properly normalized single particle states. There's one last thing to check now, which is, what about multi-particle states? Does phi x, when you act on the vacuum, does this include multi-particle states as well as single particle states? So we want to compute, say, a state with, say, total momentum p and a bunch of other quantum numbers, which I'm going to just summarize by n. Would be the momenta of the other particles. Okay, and this is the total momentum. So it's some state up in that continuum. Up here, we want to know whether phi acting on the vacuum can bring us up to some state in the multi-particle continuum. We'd like this to be 0. Unfortunately, I don't have time to argue why it's 0. So it'll just take me 10 minutes tomorrow to do that, and then we'll go on and do real scattering theory applications of this formula and calculate some cross sections.
This is the first step of the renormalization.
Yes, this is a renormalization step. Actually, the shift of phi is a type of renormalization that's called additive renormalization, and this is a multiplicative renormalization. Sometimes this is called wave function renormalization or just field renormalization. But there are other types of renormalization too.